Hi, this is Miss Erickson, and today we are taking notes on Newton's third law. So get your packets out, open up to the page that says Newton's third law, not Newton's second, Newton's third law, and get ready to take some notes. Press pause until you're ready, and then when you're ready, press play. And say, "Hi students, I'm ready to learn about Newton's third law." Newton's third law, often called action-reaction. You've probably heard for every action there's an equal and opposite reaction. Don't write that down. I don't like that definition, so I crossed it out. It's a one that you probably learned and most people know, but it's not a very good one. Here's a better one, Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So right now, Bladen's head is hitting my cheek. My cheek is exerting an equal and opposite force on Bladen's head. Action and reaction forces are equal in strength and opposite in direction. So when Bladen's head hits my cheek, or when my cheek hits Bladen's head, I push his head this way, his head pushes my cheek this way. The forces are equal and in opposite direction, and they happen at the exact same time. Okay, here we have some examples, and this is a short set of notes, so go ahead and put these examples down in your notes. You don't have to draw the picture, but a picture is nice. A picture is worth 1,000 words. So the skateboarder pushes the wall pushes the skateboarder. If you look at these arrows, they're equal in size, they're opposite in direction. The harder that skateboarder pushes the wall, the harder the wall is going to push the skateboarder, the harder the skateboarder is going to go. The runner pushes on the ground pushes on the runner. So this is the way that we run. This is if you walk or run anywhere, you push into the ground and the ground pushes you. So if you want to run faster, then you have to push the ground harder and the ground will push you harder. So you push the ground back and the ground pushes you forward. The table pushes up on the book pushes down on the table. That's another good example. The last one, gravity from Earth pulls you down in your seat. You pull the Earth up. That's one we're going to have to think about for a minute here. Okay, we're going to think about that last example. This time, instead of thinking about you, we're going to think about Bladen. So, is gravity pulling you down, Bladen? Let's see. Yep, drop test. Gravity pulls Bladen down. Every time I stop holding him up, I'm holding him up. Every time I stop holding him up, gravity pulls him down. This time I'm going to look really carefully. I'm going to see, does he pull gravity up? So let's see. I can't see it. I don't see the Earth pulling him up. So gravity comes from Earth. Earth is pulling him down. Earth is pulling me down. Earth is pulling everybody down. And welcome to the video recording.
What was this?
We're just talking about gravity. So is gravity pulling you down right now?
Gravity is bringing me down.
Now, when gravity from the Earth pulls you down, do you pull the Earth up?
To get up.
Okay, so we all agree gravity pulls us all down. Gravity pulls Bladen down. Gravity pulls my husband down. Gravity pulls you down. Gravity comes from Earth. So Newton's third law, you pull Earth up. Bladen pulls Earth up. My husband pulls Earth up. The reason we can't see you pulling Earth up, the reason we can't see Bladen pulling Earth up, it has to do with mass. Bladen is very small mass, and all of you are very small mass in comparison to the Earth. So that very, very small mass has a very, very large acceleration. The Earth has a very, very big mass, has a very, very small acceleration. So the force is the same. The force is the same. The acceleration is different. So I'm going to say that again. The force that Bladen pulls the Earth up is the same as the force that the Earth pulls Bladen down. The force is the same. The acceleration is different. Big acceleration on Bladen, small acceleration on the Earth. but that's a good trick question. You know, I love those trick questions. So the force that gravity pulls Bladen down is the same force that Bladen uses gravity to pull Earth up. So a student once told me that everything is easier to understand if you use guns as an example. So let's think about guns. When you shoot a gun, when the gun shoots the bullets, the gun pushes the bullet forward. That's the action. Then the reaction, the bullet pushes the gun back. That's the kickback. These forces are equal and opposite, and they happen at the exact same time. So the gun is pushing the bullet forward, the bullet is pushing the gun back. That kickback is happening at the exact same time. Those forces are equal. It's the exact same amount of force on the bullet as it is on the gun. The forces are exactly equal. So then the question is, how come the bullet goes 750 meters per second, but the gun only kicks back a little? And even if it's a big kickback, it's still not 750 meters per second, right? It's still not lethal. So how come they're going such different speeds? Same force, the different acceleration is because of the different mass. The bullet is tiny, 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 tiny. The gun is relatively big compared to the bullet. So more mass, the gun with the big mass is going to have a small acceleration. The bullet with the tiny, 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 tiny mass is going to have a big acceleration. Same force, different acceleration. Same force, different acceleration. So this is another really good trick question to see if you're really paying attention. Newton's third law, the forces are the same. When the gun pushes the bullet forward, the bullet pushes the gun back. The forces are equal and opposite. That's Newton's third law. The acceleration is different. So you can use the same exact, you can change this, all those words from Earth. Gravity comes from Earth. So gravity from Earth pulls you down. Gravity from you pulls Earth up. And everything else is the same. Forces are equal and opposite. Same force, different acceleration because of different masses. All right, we've been talking about action-reaction forces today. Previously, we talked about balanced forces. Both of these forces are equal and opposite, but they're different. So action-reaction happen between two objects, and they always exist. So A pushes B, B pushes A. So Bladen pushes my cheek pushes Bladen. The gun pushes the bullet pushes the gun. I push the wall pushes me. Those are action-reaction. They happen between two different objects, and they always exist. Balanced happen on the same object, and they cancel each other out. So this could be a book sitting on a table. So gravity's pulling the book down, support force is pushing the book up. These two cancel out because they act on the same object. Action-reaction will never cancel each other out. Both are equal and opposite. So if you just know that the forces are equal and opposite, you don't necessarily know which type of force we're talking about. Okay, here's some examples. These will be similar to test questions, so put these examples down in your notes. I push big boy up, gravity pulls big boy down. So the question is, these are equal and opposite forces. Are they action-reaction forces or are they balanced forces? So I don't have big boy with me today. I've got my coffee mug. So I push big boy, I push the coffee mug up. Gravity's pulling big boy, the coffee mug, down. These are balanced forces. Both forces are acting on the coffee mug, causing it to stand still. It's causing it to stay at rest. So that's an example of balanced forces. They're both acting on the same object, canceling each other out. That's balanced. A swimmer pushes the water backward. The water pushes the swimmer forward. So swimmer pushes water, water pushes swimmer. This is action-reaction. One force is acting on the swimmer, one force is acting on the water. They're pushing each other, action-reaction. Gravity pulls the flying squirrel down. Air resistance pushes the flying squirrel up. Both of these forces are acting on the flying squirrel. So one is pushing the flying squirrel down, one is pushing the flying squirrel up. These are balanced forces. The girl hits the volleyball up. The volleyball hits the girl down. So one force is acting on the girl, one force is acting on the volleyball. These are action-reaction. Girl hits volleyball, volleyball hits girl. That's action-reaction. So these are the types of questions I could ask, and then the question is this action-reaction or balanced? And you have to find the answer. Okay, this is the last slide. This is the horse and cart problem. And you'll see there's no words on this slide, but this is definitely going to be a test question. This is a famous problem. You can even look it up on the internet if you don't like my explanation. But this is definitely going to show up on the test, so you definitely need to listen and write your own notes. All right, so here's the question. The horse pulls the carts, and then we just learned from Newton's third law, if the horse pulls the cart, this P is the horse pulling the cart forward, then the cart pulls the horse backward. This P is the cart pulling the horse backward. So if the horse pulls the cart and the cart pulls the horse, and these forces are equal and opposite, the question is, how can this cart move forward? How can this horse-cart system move forward if these forces are equal and opposite? That's the question. So let's think about the answer for a second. Okay, so the reason that the horse and cart can move forward is because action-reaction forces act on different objects, so they don't cancel each other. So if we want to know if the horse moves forward, we can look at the forces on the horse. So the horse is pushing the ground is pushing the horse. That's what these big F's are for. So the horse is moving forward. The horse is getting pushed forward from the ground. The cart is pulling it back, but as long as this forward force is bigger, then the horse will move forward. Now if we look at the carts, this P is the horse pulling the cart forward. This F is friction from the ground pushing the cart backwards. As long as this P is bigger than this F, the cart will move forward. So if we look at each item separately, we can see the forces acting on the horse. The net force is to the right, so the horse is going to accelerate forward. If we look at the forces acting on the carts, the net force is to the right, so the cart is going to accelerate forward. So these action-reaction forces, they are equal and opposite, but they don't cancel because they act on two different objects. So when the horse pulls the cart pulls the horse, the forces are equal, the forces are opposite, they do not cancel, so the cart can still move forward. When we get to the test, I'm going to turn this into a multiple choice question, and one of you guys is going to say that the horse pulls with more force than the cart does. And it's going to be more than one of you. It's going to be a lot of you. And I'm telling you right now, the horse pulls with the exact same amount of force as the carts. The forces are equal. So don't be that guy. Don't say the horse pulls harder. The horse does not pull harder. The forces are equal, but they don't cancel because they act on two different objects. They don't cancel because they act on two different objects. Okay, that's it for the notes. Newton's third law, on the one hand, it's really easy. On the other hand, there are a lot of trick questions. So I think I went through and talked about some of those trick questions. So hopefully you won't be too tricked. Make sure that when you're done with your notes, you have a lot of notes. Now go back and do 3 questions in the questions column and a summary. A lot of you guys are asking me like, oh, how can I improve my grade? Oh, I need to get my grade up. Do everything in the packet. Do what I tell you to do. And that's the best way to get your grade up.